Alright, so we will continue with virtual lecture number 2 here, talking about closeout borings, and then we'll look at some of the other possible geometries that we have. So, last time we figured out how to determine the number of faces and edges, and also skeletal bonding electrons in a boring cluster. And so, let's do that for a couple more examples. And again, these equations, which is this one, 2n minus 4 equals number of faces, and three n minus 6 equals number of edges, apply only to the closeout geometry. You can't use these for the other ones that we'll get into here in a little bit. Okay, so let's look at B9H9 2 minus. So if we count the total number of electrons in this one, it's the number of borons, 9, times 3, plus number of hydrogens, 9 times 1, plus 2. And again, this is the one people usually forget to add in there at the end, because you have the minus 2 charge, which means there's a superfluous 2 electrons in here to contribute to the total. And so if you add that up, then you get 27 plus 9 plus 2, which is 38. So, if we wanted to know the number of skeletal bonding electrons, we could use the formula 2n plus 2. And if we were to do that, then that would give us 20. So note, there is another way to do this, right? It's the interplay between these two quantities here that is the key. And so, if you look at that, the difference between this number and this number is 18 electrons. We have 9 vertices, which means there's 9 boron-hydrogen bonds. These are 2 center 2 electron bonds. Those would require to use 18 electrons. So you could just determine how many vertices there are, 9, multiply it by 2, that's 18, and subtract 18 from 38 to give you 20, so they're self-consistent inside there. So if we apply our formulas for number of faces and number of edges, then those are the numbers we get. So again, this one is actually pictured also on your handout. So if you go to page 4, this is it right here. And so each one of the points, like that one at the top there, in those pictures represents a boron-hydrogen vertex. And so you see the shape of it. Again, this is done in the shorthand notation, but if we go back to our incorrect, of course, theory that this represents the number of boron-boron bonds, and we pretended that these were two-center two-electron bonds, if we did that, you'd need 42 electrons for this. And in the skeletal bonding calculation that we did, there's only 20 doing the job of what would be 42. So again, these are three-center two-electron bonds, or even more electron deficient than that. And so again, the important thing to realize was that any of these clusters, they're highly electron delocalized and highly electron efficient. Okay? So just one more example. And, hey, you can fast forward through this part, unlike my regular lectures. So not to beat the thing to death, but it's useful sometimes to see multiple examples. So let's do the classic B12H12 2-. Okay, this I know, and I also mentioned before, is an icosahedron. And if you'd like to see it, there it is right there, at the bottom of that page. And it turns out, here are several other examples of icosahedral carboranes, and we'll get into that in a bit, because what you're doing there is replacing a carbon, replacing a boron, sorry, with a carbon. So for this, the total number of valence electrons is 50. So 3 times 12 is 36, plus 12, 48, plus 2, 50. All right. And we fall to our formula 2n plus 2 for this. N is 12, so 24 plus 2 is 26. Skeletal bonding electrons. Two n minus 4 faces, that gives us 20. And that's how many faces an icosahedron should have. And so again, the formula does work. So here we're going to have 36 minus 6. 30 edges. So there's 4 things you should be able to calculate. And these are they. The total number of valence electrons, the total number of electrons used for skeletal bonding, either using the formula or determining that there are 12 vertices. That takes 24 electrons, and subtract 24 from 50. The number of faces and the number of edges. So these are things that you need to know, especially for exam 2. So once we have that out of the way, again, if we look at this and say, if we had 30 two-center, two-electron bonds, we need 60 electrons to get the job done to hold the whole thing together. Of course, that's not the case. What we have is only 26. So just compare that for a second. Now look how drastic that's becoming. Right? The number between what you'd expect for two-center, two-electron bonding and the actual number holding the thing together they're becoming farther and farther apart, they're diverging. And so that's also an important message that we should keep in mind. And you can summarize that like this. as the cluster size increases, the cluster becomes more delocalized, and more electron deficient. That leads into a whole bunch of properties for these things that are of pretty significant interest. We'll actually look at only one of them, and we'll get to that in a little bit. But this influences their optical and electronic properties, obviously, because the number of electrons you have roaming around within the cluster framework is a lot smaller than you'd expect, especially as the clusters get larger. So this statement right here is a good one to know, but it's really obvious when you're doing these calculations that that's what's going on. All right, so the next important thing and kind of major topic is this one, the related structures. And by this, what we mean is nido or arachno. And so what these are derivatives of the closo structures, where one, in the case of nido, or two, in the case of arachno, vertices are actually removed, giving a more open structure. And so you don't have one of these nice, pleasing geometrical structures. You've got something that looks a little bit different. And so for this, there's 2 pages of the handout that are relevant. Let me show you which ones they are. The first is this one, and we'll talk about this in a few minutes. But this is the classic diagram that everybody uses, actually from Rudolph's Accounts of Chemical Research article. So there's the reference for that if you actually want to go look it up and read it. But it's a little simpler, again, to go with this page here, so you can see what's going on when you start removing vertices and the like. Okay? So we'll do the if you will, Gedanken thought experiment to get to those structures in a second, but let's define them and see what their formula are. So start with nido. This is the closo structure missing one vertex. So one boron hydrogen vertex is going to be, if you will, plucked away from the structure. And when you do that, you've got to provide electron density back. And so if we take away one of these vertices, which has 4 valence electrons, you've got to give the cluster back 4 electrons. So the closo structure is missing one BH vertex, and it has 4 extra hydrogens. And so in words, this is what we're doing. We're taking away one vertex, one BH vertex, and we're going to put 4 hydrogens back on after we do that. And so when you translate that into the formula, As we had for Clozo, a general formula BnHn overall net charge 2 minus, we have a general formula for this too. And that is BnHn plus 4. So for example, if I had a cluster and I knew its geometry was a nido structure, and I had in there 6 borons, that's this n plus 4, 10. Now we're going to use the Wade-Mingos rules, which are actually on the first page of the handout that I gave you, to be able to predict this. But once you get the hang of this, you'll look at a formula like that and say, aha, that's a nido structure. So again, there are formula if that's your thing, you like to drive things in that, or if you know more memorization or be able to recognize things. Your nido structure is always going to have n borons and n plus 4 hydrogens attached to it. Now, there can be charged ones as well. This formula is the most common, but there are situations where you can have this here. BnHn plus 3 with a -1 charge. We're not going to see too many examples of that, but just be aware if you run into this stuff again, that is also a general formula for a nido structure. All right. So then, what about the other one? Arachno. The general formula for this is not BnHn plus 4, but rather BnHn plus 6. And so it has 6, if you will, extra hydrogens. This is derived from a nido structure by taking away one vertex, one BH vertex, and then adding to it 2 more hydrogens. And you'll see how that works in a second. Okay. So, what's an example of this? That one. B10H16 is an arachno structure. Now again, the Wade-Mingos rules will tell you that, but it's usually pretty straightforward to eyeball it and say, okay, that's what it is. You can also have a structure BnHn plus 5 with a net -1 charge on it, but again, that is a lot less common. Okay? So, what is this deal? Why are we saying these are related structures? Well, they're all related to a parent Clozo cluster. So let's check out the more simple example in detail here, and then we can go back to the previous page, this one, and see how this all works together. Okay? So, this one is nice because it has everything drawn on it for you. So let's see what happens. Let's start with the parent structure. This one is Clozo, as we know now. And if you look at the picture, on this. Okay. One thing to note, is the following thing. All of the boron-hydrogen bonds are terminal ones. There are no bridging BHB linkages in here, and so all of these terminal bonds are two center, two electron. And it's important to distinguish that because that will come into play for one of the types of chemistry that we're going to look at for these things. Okay. Now, how do I, again, in a thought experiment, chemically you don't really do this, convert this to its related nido structure? Well, that's what all the business is here on top of the arrow. And so let's go through that stepwise, even though it might be quite obvious what's happening. The first step is we're going to remove a vertex. Now, it could be any vertex you want because they're all related symmetrically. So, in the picture, you see they take out the bottom one. So if you do that, you're left with B5H5 2-. So the first step, which is shown right there, minus BH, gives us this. Okay, now, we said this has got 4 hydrogens extra, so that's what we'll do now. Is we're going to add 4 hydrogens. Now what we've got left is this formula. And then the final step is to take 2 electrons away. And when you do, there you go. Note that that does fit the general formula that we had. BNHN plus 4, no charge. So it's a little more complicated than popping one vertex off. It's actually 3 steps, but these are they in turn. And so now we're at this point here. So we're now at the nido cluster, which now is drawn out to show you exactly what's going on. So if I were to ask you, and I will, it's actually on the homework, okay, what's the related nido cluster to this closo cluster? That's how you arrive at the answer. It doesn't matter where you start, and don't worry, we'll do an example or 2 going both ways for this. And so if we now take a look-see at our structure, again, it's drawn here. This is the middle part of the page. Where did those, I'm out of picture, sorry. Where did those 4 hydrogens end up? Well, if you look at again what happened, that bottom boron hydrogen was abstracted, and we have 1, 2, 3, 4 bridging hydrogens attached. And so this has five terminal BHs. And 4 bridging BHB. This fits into the convention that we had before. The terminal boron-hydrogen bonds are still, as always has been, 2 center, 2 electron bonds. The bridging ones are 3 center, 2 electron bonds. 3 center, 2 electron bonds. And so those are constructed exactly as we did in class on Monday, the 18th of February, for the B2H6 diamond. But it just happens in this case 4 times. And it's a little more complicated because you have bridging hydrogens at the same boron and all that sort of thing. But no matter what, this is still true. 3 center, 2 electron. These chemically, as you might imagine, are different than those terminal ones are, as we'll see. Okay? So that's the NIDO one. You might wonder, what the heck does NIDO mean? It means nest, like. So somebody with a really good imagination or a sixth sense of humor, I'm not sure which, the side of that looks like a bird's nest. So there you go, that's all that means. What then are we going to do next? Let's get the related arachno structure related to this NIDO structure, which is in turn related to the B6H6 2- closo structure. Okay, so that's what we're going to do next. This involves removing yet another vertex from the NIDO structure, or in a net effect, you're removing 2 vertices from the closo B6H6 2- ion. So if we follow the steps stepwise, off with a BH, that's going to bring us down to B4H8, and then we're going to stick 2 hydrogens on there. B4H10. And so from that, then, you can see that that fits our general formula, BN, H, N plus 6, so 4 plus 6 is 10. So it does fit the arachno formula, which is good. So, if you were asked to take a NIDO structure and turn it into its related arachno structure, this is what you do. You take a BH off, you add 2 hydrogens, and you arrive at that. You can start all the way from the closo through the NIDO to the arachno, and want to be able to go back the other way too. So, again, what does this term mean? Spiderweb. So, I don't know, does it look like that? Maybe. But one thing to do notice here in this is that if you look at the structure there, it's very open. And so the closal structures are tightly knit, geometrically sealed, essentially, structures, and they become more and more open as you go from closo to NIDO and finally to arachno. So the arachno ones usually will have these really kind of strange shapes to them. And so our bridging hydrogens are here, and our terminal hydrogens are there. So notice what's going on with this before we move along. There's 4 bridging hydrogens with it. And 6 terminal hydrogens. In fact, some of the boron-boron bonds, if you notice in here, have been disrupted as well. Whereas in our NIDO structure, we've still got all the borons are attached to one another. Here, this one's off by its lonesome self, and so is that one. And so to compensate for that, that's why you need the extra terminal hydrogens. It's actually beyond the scope of what we're doing to predict how this turns out for all the other complicated structures that you get. It's usually easy to see what happens when you go from closo to nido in terms of where you place the bridging hydrogens. But with these, it's much more difficult. So again, I wouldn't worry about that. But you should be able to count the electrons and everything like that with it to see how that goes. Okay, so if we now go to this picture, the famous drawing everybody steals, obviously including me, from the literature. Let's look at what's going on. In this first column, right here, you have closo structures. Here, you have nido structures. And here, you have arachno structures. So I can write that on there if you can actually read it. All right. Closo, nido, arachno. The diagonal lines are telling you that this arachno structure is related to that nido structure, which is in turn related to that closo structure. And so this is a simplified version of what we just did. The structure at the top here this one right here is B4H4 2-. It's a tetrahedron. And so all of the things that we said about closo structure should apply to that as well. Does it have 4 sides? Yeah. Does it have 4 vertices? It sure does. All right. So we start at 4 and go all the way down to 12 at the bottom. 4 borons, 5 borons, 6 borons, 7 borons, 8, 9, 10, 11, 12. There's our icosahedron. You can go further. It's just that those things start to get really tough to draw. All right. So let's start with an arachno structure and figure out what's the related nido and what's the related closo. So we're going in reverse of what we did before. So I'm just going to make up a number here. B6H12. This is arachno. So it's one of the ones over here in the right-hand column. Now, if you can count the spheres, you already know which one this is, right? But let's save that for the end. No peeking, okay? Because what we want to do is figure out the formula of our, pardon me, related nido and then closo structure. So let's do it. Let's turn this into its parent, if you will, nido structure. What do I got to do first? Well, I have to remove, so I'm pointing here, the 2 hydrogens that I put on to go from nido to arachno. And I've got to add a BH. Now you can see how silly all of this actually is to do over and over maybe, because I'm taking a hydrogen away and I'm putting a hydrogen on, so you could simplify this down if you like. I won't, because I want to make sure everybody's on the same page. Okay. So if we take 2 hydrogens away, we have B6H10, then we're going to have B7 H11. And does that fit the formula of a nido cluster? Yeah, it does. And then to go to the closo, what we got to do is we'll do 3 steps. You take 4 hydrogens away. You add a boron hydrogen vertex. And you add 2 electrons. So all we're doing are these 2 steps, but in reverse, with a different cluster too. And so when I do that, then I get the closo structure out. So referring back to our handy chart here, even if you don't count the things up, this is 4, 5, 6, 7, 8. So this is where we started. So the one that we just did is this one right here. Straight from the 5th one down. So that's how these are interrelated to one another. Now, how do you know if something is closonido or arachno? That's the last step right here on the bottom of this page, which again, you can probably cite, read, making another musical analogy, the formula to figure it out, unless I give you something that's maybe not so clear. So let's take a quick look at how one determines this to be. The Wade-Mingos rules. And so normally, a lot of times these are just called Wade's rules, kind of like Wayne's World, I don't know. But Mingos should get some credit for this too, as he's one of the theoreticians that developed this. And so what we're talking about here, we're applying in a narrow scope just to boranes. However, this is applicable to any deltahedral cluster, including very large transition metal clusters, very large main group clusters. Deltahedral, of course, means they have to have the equilateral triangle faces, and so these things can be generally applied, but again, we're going to worry about this only for boron itself. So you can read along on the sheet here, but a closo structure has 4n plus 2 valence electrons. A nido structure has 4n plus 4. And an arachno has 4n plus 6. So, with the boron clusters, this is pretty straightforward. Right? You already know probably by inspection, okay, this is true, this fits. But actually the geometry is determined by 2 things, the number of vertices and the number of total electrons. So let's test one of these just to make sure we're doing it right. Let's go crazy and get something very large in here. How about this one? B18H24. Now, if you've been paying attention, You already know the geometry of that. But let's apply the Wade-Mingos rules to this, just in case, let's say, we didn't know what was going on. We'll give you an example next where you don't necessarily know what's going on. So, take a look at the formula. All right. How many valence electrons does it have? So what do we have? 24 here. I have to do math in my head. Always a scary proposition when I believe that number is 72. Is it? Nope. So we all become too dependent on calculators. So there's your total number of electrons, 78. Does this fit the Wade-Mingos rules? Can we figure out what we're doing here? Well, which of these does it fit? Well, you can test each one individually, or you can save yourself some time. Noting that this part of all three equations is the same. So I could make one general equation out of these three, quite simply 4n plus x equals the number of valence electrons. So applying this to our total here, solve for x. If it's 2, it's closo. If it's 4, it's nido. If it's 6, it's arachno. So let's do this. Remember, n is the number of vertices. So, oh, I'm in real trouble now. 4 times 18, what is that? Well, it's 32 plus 40, or 72. X is 6. That's arachno. So, now you know, hopefully, how to apply the Wade-Mingos rules to this type of stuff. So, we're running almost 45 minutes here, so we'll take a break. And when we come back, we'll look at the chemistry of some of these things. Only a couple of different reactions that are really simple enough for us to put in a general sense. And then we'll look at carboranes, which is where you'll actually have to probably use the Wade-Mingos rules to figure out what the geometry of a certain cluster is.